Good job, Aiden.
I know, I was gonna text you because I had in the shower last night.
Couldn't figure it out. Huh?
I'm disappointed in your lack of time.
Yeah, no, well.
I know,
Yeah, well,
and my tie-dye stuff is like cringy. Oh man. All I have is my Sagewood tie-dye shirt. And
I didn't know it
cannot wear
was
that.
Spirit Week, so.
Wait, on Friday.
I did it!
What does Jersey Day mean?
Well, then you need to follow me at Quadratics.
Okay, bet.
Quality Instagram.
I'll never see you.
Quality.
Such quality. That's all I put up.
I'll do it.
All right, ladies and gentlemen. Good morning. Let's vámonos.
That's not fair. You're in singing. You're like the first one.
Yeah, you know.
That's true. Well then, so then join it. All right, so let's do this. How did the chapter 1 test go? Okay, what I did is I put something for you to do tomorrow. You'll see it in the announcements for tomorrow. It'll be, it's up there for cohort B today, but just kind of a quick recap. Don't look at that. That means nothing. That's other class. Here, I'll plug you in. Fine. You want to see it? Let's do it. Let me share my screen so everybody can see it. Ta-da! Hello. All right. All right. For you tomorrow,
I didn't even target your notes.
4 a.m. You guys are obviously up at 4 a.m. checking Canvas. I fell asleep in bed with my laptop on my lap last night. It was so bad.
You're not getting enough sleep.
I'm not. It's bad. It's so bad.
I know why I'm up.
What you want to do tomorrow, part of what you'll do tomorrow, I mean, part of your work for Tuesday will be homework for Wednesday. But there's just a reflection about like chapter 1 as a whole, chapter 1 test, just kind of all parts of that, because I want to hear from you. And there's also where's it going? Oh, a question about how you think you actually did on the test. Like, what grade do you think you're going to get? I'm curious to see how close you get to grades versus. And it'll probably take me this week to get all that stuff graded and back to you. I have a quiz from Algebra 2 that I have to get from last week that I need to grade. So they go in order. So give me some time to get that done. I'm going to try to do it via Canvas on my iPad where I can write on your work. Rather than like typing comments and you having to figure out what it all means. Hopefully it'll work out pretty well. So we'll see how that goes. But this will be sitting there kind of waiting for you for chapter 1 stuff. But here we are, chapter 2. Let's do it. Take us on the right way so we can write on. We have no time to spare. Chapter 2 begins right now. I'm going to bring you back over. 2.
Oh yeah.
2.1 is where we'll start. But you're not going to see much of 2.1 in the first half of class, but you'll see it in a second. I'm going to stop sharing. And Riley can see. No.
That's a lot. Like, what word would not work?
So, stack of books deal here.
I know.
Yeah.
Oh, same. Don't even know why.
Where's your tie-dye?
We all just stay quiet.
You're next.
Now
Here we go.
Grace,
This one. This one. All right. 2.1. Yeah, here we go. Is quadratics. But there's some stuff I have to do first before we can even talk about quadratics. And There we go. To make sure I didn't miss anything, I took pictures of what I did during second because I just kind of started talking and words came out, and I don't want to forget any of those words. So I took pictures. Okay. So this chapter is kind of split into two. It's polynomials for the first half, then it kind of gets into a little thing, and then rational functions for the second half. And they start talking about quadratics, but so we're just going to talk polynomials first. And for the next couple weeks, probably. We won't get into rationals, my guess, until maybe end of next week. We'll see how things go, but like 2.1, 2.2, 2.3, all polynomial stuff. And there's probably going to be a bunch of new things. Today, not so much. Today's not super new, but there might be some things that come up. So let's just talk about this word first. What does that mean?
Many names.
Not bad, right? Poly meaning many. And then nomial sounds like names, right? Not a bad way to talk about that, right? But more mathematical. Poly meaning many, nomial meaning terms. Now, I have to put the word many in quotations here because it really just means one or more. One to me does not sound like poly. What do we call, not polynomials, but if there was just one term like x or 3 or 2x squared?
Monomials. Right?
Monomials, yeah, if it's just one, it's a monomial. Right? I am in a monogamous relationship, not a polygamous relationship. I'm a one-woman. That would be so weird. I can only handle one wife. I don't know how I would be able to handle two. Okay, cool. And so, I think what we should just kind of start thinking about is how we tell different polynomials apart from one another. And the way that we classify them, it's by their largest exponent. By their largest exponent. Okay, that's what makes us talk differently or expect even just different things from one polynomial to the next. Depends on its largest exponent. Okay, and we have a name for that. The largest exponent in a polynomial. Whether it's written a long way, which is usually the way we'll see it, kind of, no parentheses, just written out long. We call that the degree. DE. The degree of that polynomial. And so let's do it. Let's look at, I'm way over here, and talk about different kinds of polynomials. Okay, so let's go f of x. And I don't know, like what's the simplest equation for a function that you could think of? Like as super simple as it could possibly get. X squared, go simpler. X simpler.
1.
1? Sure. F of x equals just a number. Just a single number. Now, we picked 1, it could have been 5 or 3 or -7 or pi or 1/3, it's just a number. Now, when I say largest exponent, it's the largest exponent for x. Okay? Largest exponent of x. Some variable, not some number, right? Because 2 to the 3rd is really just 8. So I don't want to say that, oh, the exponent is 3. No, it's 8 to the 1st, right? So what is the exponent for x here if there is no x? Yeah, this is 1x to the 0. Equals. This is 1x to the 0. This is degree 0. And let's give it a name. I know I left a bunch of space. Things are going to get a little longer. Well, what shape? If you're going to draw the graph f of x equals 1, what would that look like? How about that? Nice, I love that. Perfect. So look at that. So describe that to me. What is that?
0 slope.
Zero slope, some horizontal line. Okay, but it has its own name because it's linear, but it's just flat. So we don't call it linear, even though it makes a line. We just get a little bit more specific because it's degree 0 and it's perfectly flat. Let me know before I lead you there. Is the y value changing at all? What do we call something that's not changing? These functions are actually called constant functions. Okay. Yeah, of course, they make a straight line. They go on forever. Right? Domain is infinite, but the y value will never change. It's always 1 or 3 or -5. Yay, good. Degree 0, done. What's the next degree we should probably talk about? 1. Let's just go up by 1. Okay. So let's come up with a function whose largest exponent, right, whose degree, I'm going to say degree the rest of the way, is 1. X. Perfect. Right? And that's about as simple as it can get, right? Plain old x. Now, but do you agree that x plus 3 is also degree 1? What about 2x plus 3? Is that cool too? Why not, right? Because it's all about the exponent. Good. I'm going to use 2x plus 3 because it's just a little more interesting than just plain old x. Looks kind of weird, the equal sign. What is that? It's like half of an angry face. Because I was like drawing that. What kind of function is that? There it is. I like to song and dance. Here we go. Okay, cool. Okay, yay, done. We know linear functions. We just spent most of chapter 1 talking about it. What's next? What degree should we go up to next? Okay, h of x. I'm just making up the names. Doesn't matter. Give me a function whose degree is 2. X squared, 2x squared plus what?
3.
Plus 3, absolutely, right? We can mess with as much as we want in terms of what we're adding, subtracting, multiplying, and dividing by. I don't know, 3x squared minus 6x plus 4, right? Isn't that still degree 2? Largest exponent, right? Beautiful. Degree 2, what do we call that? And most of chapter 1 kind of focuses on these. Section 1 of chapter 2, sorry. 2.1 is all about quadratics. And so we'll spend some time today kind of going back through Algebra 1, Algebra 2 to make sure that all of those quadratic skills, we refresh those. Because there's a lot of things about parabolas, about quadratic functions that are just unique to quadratics. Okay? But this list, you can keep going. Today we're going to stop right there and talk about quadratics, but we can fill in these degrees forever. I mean, degree 3, degree 4, degree 10, degree 30, degree 4 million. It's still a polynomial. Okay? Cool. Now that we've got ourselves kind of a specific list, let's talk about polynomials in general. And we're going to also a general form for what makes a polynomial. You come with me. Ta-da. Can you see that okay? Polynomials in general. And I don't know, call it P of x for polynomial. Now you're gonna want space. I'm gonna come all the way here. Okay, so make sure you're not right into it. Okay. And we're not going to put any specific numbers in there like we did for those 3 examples. Right, 1 or 2x plus 3 or 3x squared plus blah, blah, blah. I want to just drop all the numbers and talk a little bit more in general, be a little less specific. Okay. And so to talk about the degree of whatever this polynomial is that we don't have any numbers for. I can't use a number. And so I'm going to use the letter n. When I talk about the degree of a function, it's going to be, in general, degree n. Why n? Because it's just a number. Okay? Did we talk about 1/2 or 2/3 or pi over 7? I don't want the square root of 6 as a degree for something, right? Because when we talk about degrees, I want these numbers to be integers greater than or equal to 0. Okay? Polynomials do not have fractional or decimal or irrational exponents anywhere. And I'm not talking just the largest one, but any of them, okay? Because if I said something like x, and I might have done this before in here, I forget, like x to the 2/3, right? Power over root. Take your head up and down if you know what I'm talking about, and if not, right? Power, x squared, root of 3, right? That is not a polynomial, okay? Because it's got an exponent that we don't like. Okay? As nice as 2/3 is, it's not going to create the kind of graph that we like and allow us to do things with polynomials that we're looking forward to. So when we talk about degrees, I want to make them nice, not quite so nice, although we love those. I want things to be really good, okay? And so let's put this in general form of a polynomial, kind of in the same order that we've been putting these. No parentheses, nothing like that. And let's just put the largest exponent first, and then work our way down from there. But I just don't know what that exponent is because I don't care what it is just yet, okay? Leave a little space here. So we're going to put something right there. So leave a little space. But let's just put x to the power of, and let's put the biggest power that it's going to be. Let's put the degree of this polynomial. Let's put the largest exponent here first. Well, I don't know what it is, so I'm just going to call it n. X to the n. Okay, leave some space. And there's a polynomial. That could be enough. But in general, there might be some more. Right? We might add or subtract some stuff after that, but it's going to take us down into lower and lower exponents. So put a little plus sign and leave some space. Okay? And let's put an x right here. And we'll figure out what that exponent, what we could call that. Well, if this n right here, let's say, was a 2, like that quadratic, is it okay if this is a 1? Is it okay to put like a plus 5x afterwards and it's still quadratic? Okay, cool. If this was a 3, could this be a 2? If this is a 10, could this be a 9? This was 100, could this be 99? So if this is n, what is the next closest number that I can put right there? N minus 1. Okay. We can go down by 1 each time, but I don't want to go down by a half or a third or pipes, ninths, whatever, right? I want really nice numbers. Cool. Okay, put a plus. Because there could be more. Leave a space. We're going to fill that in a second. Okay. So x to the power of, well, okay, so 10, 9. Could this be an 8? It's not going to be a 9 again because that's not simplest. I want to simplify things. So I'm not going to have any repeated exponents, but 10, 9, 8. Okay, so what do we call that exponent? If this is n, and then n minus 1, and I can just keep going. N minus 3, n minus 4, n minus 5, all the way down, but I don't know how many there are. But what I do know is that there's going to be an end somewhere because my degree can't be smaller than 0. So I can go 100, 99, 98, 97, 96, 95. Now, I don't have to have each one though, right? Like, I could get rid of that minus 6x. Is this still quadratic? Yeah, because there's a plus 0x to the first. So there is an x to the first term, but its coefficient with it is just 0. Okay, cool. So I'm going to do this. I'm going to put a plus, and then I'm going to put dot, dot, dot. Because I don't know how many there are in between. But what I do know is that this thing is going to end. So I'm not going to leave it as plus dot, dot, dot. I'm going to put an end to this here. And normally when we have an unknown number of anything, we like to have 2 or 3 to start, usually 3. Because that'll give us a pattern. and then like 1 or 2 at the end. So I know where things are going to end. So I'm going to do 2. So leave a space. Okay. Plus x, and then leave a space, and then plus x. So I've got blanks all over the place. I'm going to put something there and there, right in front of every single one of these x's. But I have to figure out what exponents I should have as my last 2. The second smallest number I could possibly use for an exponent, and then the smallest. Blaine.
Would be n minus n plus n minus n minus 1.
Okay. N minus, like, 10 minus 9, or 100 minus 99, or 1,000,000 minus 99999, right?
Yep.
Okay, well, what's n minus n plus 1? Because that's what you did, right? N minus 1. Well, what's n minus n? What's 5 minus 5? What's n minus 10?
0.
The second smallest exponent I could have anywhere can just be a 1. It's going to be some linear term. And so let's just write the 1. Perfectly, that's perfect. But that's even simpler. So let's just call it x to the first. And then 1 less than that, x to the 0. Okay? And so we've got these polynomials that could go on for a long time, but there will be a beginning and an end to them. But what's most important to me, the thing that's going to drive the behavior of this function, the way it's going to look, how many times it could hit the x-axis, how many times it could turn, how many vertices and hills and bumps it could possibly have, it's all about this right here. But what we notice is that every single one of these x's could have some number attached to it by multiplication or division. We call it multiplication of fractions. So I want to put something in each one of these spots as a coefficient for that variable. And they could all be different, they could all be the same, doesn't matter. But I want to relate them to the x that they're connected to. So I want the coefficient for x to the n to be related to x to the n. And x to the n minus 1, I want it to be related. Okay? And so what we're going to do is we're going to drop something in each one of those spots that relates us back to where we are in this order. Now, letters at the end of the alphabet are usually for variables, x, y's, and z's, for things that we don't know, and we can put in anything we want. Letters at the beginning of the alphabet, a's, b's, and c's, are for unknown constants. Things in general that once I pick them, they stay for that function, right? 3, 0, 4. 2 and 3, even 1, right? That was that constant that it didn't matter whether I wrote 1 or 3 or -5, right? It's still a constant function. 2 or -2x plus 3, it's still a linear function, right? That didn't change. So let's pick a letter at the beginning of the alphabet for our unknown constants. Where should we start? Hooray! A sounds great. But here's the problem with me going A, B, C, D, all the way down. What if I have 27 terms? I run out of letters, and I've used x, which is no good. And I don't know how many I've got. So I don't want to do that. So instead of naming them all different letters, let's do what we've done in the past for when we talked about 2 different points. And we tried to tell the x values apart, right? x1, y1 versus x2, y2. But you see, I don't really have numbers in here except for these. So we got to be careful how we do it. So here's what we'll do first. Every single one of these spots is going to have the letter A. But we need to throw a little subscript number attached to each one of those so that we can tell them apart. Okay? So I'm going to drop in some A's. I'm going to lose these. But leave a little space because we need a little space for some subscript stuff. And I just want them to be different. I don't want every variable, every constant, every coefficient. I don't want those to all be the same. I want to relate it back to the term that it came with. If this is x to the n, what subscript could we put so we know that this came with this one, 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 that this came with this one? A sub n, x to the n. the degree of that term and the subscript is exactly the same. So if this is x to the n minus 1, what should we call the subscript for this one? A sub n minus 1, n minus 2, a sub 1, a sub 0. And so the exponent, the degree of that term, and the coefficient, the names just match really well. Cool? So that's just kind of in general, so I can talk about n and a sub n minus 3, and you know what I'm talking about. Cool. Did I miss anything? Gotta check my notes. So far, so good. Anything super new besides, I mean obviously that's kind of new. All good? Sweet. All right, let's do quadratics. All right. You come with me. Yeah. Center you up. Okay. Ta-da. All right, quadratics. Here's where I hope you tell me some stuff, unless if it's going the other way. Tell me what you know, and I'll fill in the rest. What do you remember about anything related to quadratic functions? Ubasta.
For every x1, there's an x minus part. Or there's a negative for every positive.
What do you mean by that? The negative for every positive.
Like in the function x2, there'd be x1, it's mirrored.
Ah, so there's
Symmetry.
symmetry. Right. And the shape that you're talking about that gives you that symmetry,
Is a parabola.
parabola. And I mean, parabolas are everywhere. The reason these lights work, parabolas. The reason your phone works, parabolas. I mean, look at the light on Squishy's cage there, that black thing with the red sticking out. What is the shape of the black cone? Oh, it's a parabolic, right? I mean, think of satellite dishes. They have a focus, right? You've got this dish and it's got this thing in the center. It's got reflective properties, so that no matter where the satellite's data is being beamed from, whatever direction it's going, once it hits that satellite, it gets reflected back to the focus. Comes from here, boom, right back to the focus. They're great. I mean, projectile motion throws things up, they come down. What shape do they make? Correct. So they're really interesting to study in all their properties. And symmetry is a big part of what makes them worthwhile, right? Every parabola has symmetry. And we'll talk a little bit more about specifics to that symmetry in a little bit. Good. What else do you know?
Got a vertex.
Got a vertex, beautiful. A vertex, it's a point, right? It's some xy, where it runs into the bottom of the parabola or the top. And how do you know what that, I'm going to call it orientation? Whether it opens upward or downward. Do you remember how we know, like if this is true, then it opens upward, and if this is true, then it opens downward. You remember how to tell which direction it's facing? I mean, you can go back, you have this example.
Positive and negative.
Positive and negative what?
That first coefficient.
The leading coefficient, whether it's positive or negative. Well, if we're looking at a quadratic, and we're talking about its leading coefficient, if the term we care about is the x squared term, but I don't know what this number is, how could I name that coefficient? The term, the coefficient of x to the second power, based on that in general form we just wrote. A sub 2. If a sub 2 is, if a sub 2 is positive, is greater than 0, it goes up. If a sub 2 is less than 0, it goes down. Okay, good. Nice, we did it. All right. Okay, good. Do you know how to find the vertex without the graph. Like if they gave us a quadratic in what's called standard form. Yeah.
Negative b over 2.
Oh, amazing. The vertex. There is a really easy way to find it if it's written like that. No parentheses, no anything else like that. Now you probably have seen it written ax squared plus bx plus c rather than a sub 2, a sub 1, and a sub 0. This is less confusing for algebra students, not honors pre-calc students. The vertex, always, negative b over 2a is the x value. So whatever those numbers are, whatever b is, change the sign and divide it by 2 times whatever a is. And we'll work through an example. See it? And then to find the y value, just plug it back in. F of negative b. Just plug it back. Sweet. Nice. Okay. All right, so at some point xy, but if it's written like this, and I call it standard form, and forever I've always heard it called standard form. And then I open this book, and they call something else standard form. I've never heard it called standard form before. I've always heard this called standard form. And so I'm going to call this standard form. And to the 7 PhD authors of that, I say, sorry, whatever, too bad. That's what I'm going to call it. You're going to have to deal with it, all right? So standard form, ax squared plus bx plus c, and there's the vertex right there. Okay, cool. Let's talk about that symmetry that Blaine was talking about, right? You've got this perfect middle, right, somewhere. What is that dotted line called that I just drew? That splits this thing down the middle. Yeah, the line that where the symmetry is, yeah, let's call that the line of symmetry. I like that. A little fancier, we call it the axis of symmetry, but line of symmetry is cool too. The axis of symmetry. Well, if you've got, I don't know, some parabola floating around space somewhere, and you've got this line, whatever, close enough, and you've got this line that cuts it right down the middle. Wherever that happens to be, which axis do you know a vertical line has to run into only?
X.
The only one is going to be x, right? The only time I'm ever going to actually be the y-axis as a line of symmetry is if it's the y-axis. So the only variable that I need in that equation is just x. Right, that goes back to chapter 1. We talked about those vertical lines only running into the x-axis. So when you write the equation for the line of symmetry, it always starts x equals. And the beautiful part is if you know the vertex, that's the number. Because this number right here, where it runs into the vertex, is the same as that number where it runs into the x-axis. So you know you're good. So if you can find the vertex, you know the axis of symmetry without having to do any work. I'm really just going to be looking for x equals. Gotta see the x equals. Cool. Let's stick with this standard form thing. Do you know where the y-intercept is going to be on that f of x up there without any numbers? At some point where I'm going to run into the y-axis somewhere. Does every parabola have to hit the y-intercept? The y-axis on it. So, can you draw a parabola that does not hit the y-axis? Can you draw a parabola that does not run into that? Yeah, me neither. Why? Because they go out. Whether they're going up and out or down and out depends on that orientation. But there's always going to be a y-intercept. And so it could be there. It could be somewhere, it could be way up there. But what do you know if you're on the y-axis? What's the x value at every single one of those points? 0, yeah. I haven't moved left or right, I'm only going up or down. So it's gonna be 0, comma something. And so look back at f of x and let's plug in 0. What's the only thing left after you plug in 0 everywhere? 0, 0. See? Whatever that last number is, whatever your a sub 0 is, there's your y-intercept. What about x-intercepts? Now I'm going to put the s in parentheses here. Does this graph, this little one over here, has 2 x-intercepts? Right, you got one right there, one right there. Can you draw a graph of a function, a parabola, that only has 1 x-intercept?
Yeah.
Sure. How about y equals x squared, right? The parent function, ooh, that was cool. It only has to hit once. So there could be 2 or there could be 1. Could there be 0? Could you draw a parabola that doesn't hit the x-axis at all?
Yeah.
Sure, right? Because it's got this turning point, whether it's upside down or right side up, doesn't matter. I'm going to do positive orientation. How about that one, right? So that's why I put the s in parentheses there, because there could be 1, there could be 2, there could be none. How are we going to find out?
Factors.
Factor what?
The coefficients usually.
What do you mean? Yeah, let's make one. Let's make one up. Let's do a real one. F of x equals x squared plus 5x minus 14. Let's do a real one. Well, first, before we get into that, what's the y-intercept?
-14.
And you can just say -14, that's cool. You don't have to say 0, comma, -14. It's understood. I asked for the y-intercept, of course x is 0. I get that. Where's the vertex? The best way to do that when it's written in standard form is to do -b over 2a. Take this number, change the sign, and divide it by 2 times whatever this number is right here, right? -b over 2a, so -5/2 or -2.5, and then plug it back in. We're not going to see it, but cool. Got that? -b over 2a. Good. Where is the axis of symmetry?
-5/2.
There's one thing I'm always looking for the equation for the axis of symmetry. Say it again. X equals. Just start like that. Because I want the vertical line. I want to know that part exactly. Cool. All right. Now, yes. All right. So you said factor. What do we factor? And why are we even talking about factor? Let's back up a quick second and talk about the end result that we're looking for. If you are on the y-axis, I know x has got to be 0 because I haven't gone left to right. Well, if you're hugging the x-axis here, what do you know about the y value?
0.
That's 0. This is what we're trying to figure out. And there's no easy thing for me to put in that little question mark spot right there. It's either a process or it's a form. But let's do it. Let's take this function and we should set something up so we have a reason to factor. We need an equation to solve. What should we do? Yeah, let's make y 0, right? And that's kind of what we did when we found the y-intercept. We just said, oh, well, I can just plug in 0. What we're doing here is we're saying, oh, f of 0 equals, and we did some work to go along with x-intercepts. Now we're saying, like, f of x is 0. Like, let's set y equal to 0, x squared plus 5x minus 14 equals 0, and then we solve. Now, why can't I just, I don't know, like add 14 and start solving for x? Why can't I just solve that equation with like adding, subtracting, multiplying, and dividing, and just getting x equals when I'm done? The exponent? Well, so, like if it was just x squared minus 14, couldn't we like add 14 and then take the square root to solve for x? Or if it was just the 5x, like add 14 divided by 5, solve for it? It's having both of them that screws us up. So we don't always have to factor, but when you have terms that have different degrees, you can't solve for x directly. We're going to have to factor. So I want to make sure you can do that. Now, this is when a is 1. Okay, when a is different than 1, there's just a bit longer of a process, and we'll hopefully see it today, and we'll get to it. Okay. So what do we do? How do we factor? I know, algebra 1 was a long time. I know. But you used it last time. Diamond problem is probably something you've seen before, right? Where they say, okay, I want two numbers that add up to b and multiply to whatever a times c is. You might have also seen it like this, like two numbers that add to b, and the same pair of numbers multiplies to whatever a times c is. So that's kind of the plan here. So I say, all right, here's my little diamond. I put b, I'm going to add up to 5, and I'm going to multiply to negative 14. And if I can figure out what two numbers does both, there are my numbers that I'm going to use. So, time for a little number puzzle. My favorite part. How do you add to 5 and multiply to negative 14 with the same pair? 7 and negative 2. Adds to 5, multiplies to negative 14. Okay, now let's use it. And what's nice about when a being equal to 1, we can right away just factor, right? And factor just means rewrite as multiplication. That's all the word factor. Just rewrite it as multiplication. Hey, nice, there's two things being multiplied together. Kind of undistributing, right? We're creating parentheses rather than getting rid of them. We're unsimplifying, we're factoring. And so what's going to go first in each one of these parentheses if we're trying to get to x squared? X and x, right? And that's what's really the only reason why we can jump right to here is because a is 1, so I know x times x is the only way for me to multiply things together and get to x squared, and then we just use the results, right? Plus 7 minus 2. So does that mean 7 and negative 2 are our x-intercepts, like when I come down here? Because I want to get to here, right? X equals something. Emily?
Basically just flip them so that the negative 7.
Because I want to create 0, right? I want to get to the point, and maybe you show a little work right here that says, you know what? If the first one is 0, well, 0 times anything is 0. Yay, I found an answer, right? And to do that, we get the opposite. So I know that negative 7 are my answers. And same thing, if the second one is 0, cool. Anything times 0 is going to be 0, and so I get two answers. And you can do one of two things. You can say, here they are, here are my two solutions. Or you can come down here and say, here is my set, my solution set. Either one's fine. But I want you to see that that's cool too. X equals these two possibilities, negative 7 or 2 and 2. It's really, can't be both at the same time. Can't be at negative 7 and at 2 at the same time. So, good. When a is 1, not so bad. And as these numbers get bigger, it's just more options to run through. But there's a solution if it's factorable. If it's not factorable, there is no solution. Doesn't mean that there isn't an answer. It just means it's not going to land so nicely on the x-axis. Okay, well, what if a isn't 1? What if we run into a leading coefficient. And I can call it a sub 2, I'll probably just call it A, B, and C. What if we had, I don't know, g of x equals 2x squared, let's do this one, minus 15x minus 8. And we'll end with this one today, right, 11:15. Let's do it all so far. Y-intercept. Where is the y-intercept for this function? -8, beautiful. You want to write 0, comma, -8, that's cool too. You don't have to. If I ask you for the y-intercept, I know it's a point, I know x is 0. -8 is perfectly fine. This is just better. Okay, orientation. Does it open up or does it open down? Upwards. This number, 2x squared, the leading coefficient, is positive. So I'm just going to draw myself a little upward facing parabola. That's good. Cool. Where is the vertex? It's all about this way. Okay. You need both A and B. So I'm going to take negative B. Well, B is already negative, so let's switch the sign. We'll get it back to positive. So 15 over, and then 2 times whatever A is. Well, A is 2 as well. So 2 times 2, 15 over 4, or 3.7. Decimals got an end to it, so feel free to use it. And then we're not going to sit here and plug that back in today, right now, because I'm short on time. But you would, and I would let the calculator do that. Please don't do that by hand, because that's 15 over 4 squared times 2, so 225 over 16 times 2, so over 8, and then negative. No, goodness, it's actually not terrible. I picked decent numbers, but it's still not all that much fun. We'll do it for real in a little bit. Where's the axis of symmetry? Oh, I heard it. Amazing. X equals what? Work's already done. You don't have to do any more work. Okay, cool. Here we go. Quick end, the x-intercepts. Let's take 2x squared minus 15x minus 8 and set it equal to 0. We want to factor when a is not 1. There's 2 ways to do it. How you organize yourself. You're doing it the same way. You're just organizing yourself one way or the other. Okay. The beginning is still the same. I'm still going to figure out what 2 numbers add to b and multiply to 8 times c. All right, so I'm still going to come over here and say, all right, I need 2 numbers that add negative 15 and multiply to negative 16. We're just going to use the results a little differently when a is not equal to 1. So, what 2 numbers add to negative 15?
Negative 16 and 1.
Good. Negative 16 and positive 1. Adds to negative 15 and multiplies to negative 16. So you get these numbers, and so don't write this. If I jumped right to here and I said x minus 16 and x plus 1, x times x is x squared, not 2x squared. Negative 16 times 1 is negative 16, not negative 8. I can't jump right into the factored version. I have to use these numbers differently. The results that I get from right there. Tell me if you recognize that. Okay, fine by me. You can use the box where the first term goes first. So let's say ax squared goes there. C goes at the end. And then these 2 terms come from us breaking apart this. So if you had ax squared plus bx plus c, we're going to split bx into 2 pieces using those coefficients, right? So I've got my little box here, and so, okay, 2x squared goes there, negative 8 goes there. Stick around for just 15 seconds. All And we're going to split up negative 15x. How are we going to do it? Like that. The only numbers that are going to work for us are negative 16x and positive 1. Take the greatest common factor in every row and column. 1x, sorry. And you see what you get. X, negative 8, 2x, 1. There's my solution. 2x plus 1 and x minus 8, and then we'll split it apart and so forth. More to come on that, and the math that's actually happening behind the scenes that I want to see it better. Okay, but check Canvas for a little bit of practice with this, perhaps. But definitely your chapter 1 reflection on how things went. This quick Google form should take you like that. Thanks everybody. Have a good day. Questions in there, Riley?
Nope, I did all good.
Awesome. All right, thank you.
Bye, thank